NENOMATICA, where mathematics meets YouTube excellence. Today we're going to explore the ninth property of inequalities, which deals with how reciprocals behave when we have positive and negative real numbers. Let's start with the first part of this property. If it is greater than 0, then 1 over a is also greater than 0. This makes intuitive sense. If we have a positive number, its reciprocal will also be positive. For example, if it equals 4, which is positive, then 1 over 4 equals 0.25, which is also positive. Let's visualize this property on a number line. Here's our number line. When it is positive, it's located somewhere to the right of 0. Let's say it is 4, which is here on our number line. The reciprocal of a, 1 over a, which is 0.25, is also positive and is located between 0 and 1. Notice that as it increases and moves further to the right, its reciprocal gets closer to 0, but always remains positive. Now, let's look at the second part of this property. If it is less than 0, then 1 over a is also less than 0. Again, this is intuitive. If we have a negative number, its reciprocal will also be negative. For example, if it equals negative 4, then 1 over a equals negative 0.25, which is negative. Let's visualize this second property on the number line. Here's our number line again. When it is negative, it's located somewhere to the left of 0. Let's say is negative 4, which is here on our number line. The reciprocal of a, 1 over a, which is negative 0.25, is also negative and is located between negative 1 and 0. Notice that as it decreases and moves further to the left, its reciprocal gets closer to 0, but always remains negative. So, to summarize what we've learned about the ninth property of inequalities, if it is greater than 0, then 1 over a is also greater than 0. And if it is less than 0, then 1 over a is also less than 0. This means that a reciprocal preserves the sign of the original number. It's important to note that we need to be careful when it equals 0, because 1 over 0 is undefined. So, this property only applies when it is non-zero. Now, let's see how we can apply this property in solving problems. Example 1. If x is less than 0 and 1 over x is greater than negative 2, find the range of x. Since x is less than 0, we know that 1 over x is also less than 0 from our property. We're told that 1 over x is greater than negative 2. So, 1 over x is between negative 2 and 0. Now we need to solve for x. Then x is between negative infinity and negative 1/2. Welcome to our math lesson on inequalities. Today we're going to learn about an important property of inequalities that allows us to manipulate fractions when solving inequality problems. This is known as the 10th property of inequalities. Let's start by understanding the property. If we have two positive values, a and b, where a is less than b, then the reciprocal relationship will be inverted. That is, 1 over a is greater than 1 over b, and both are greater than 0. Now, let's look at the case where both values are negative. If b is less than a, and both are less than 0, then 1 over b is greater than 1 over a, and both are less than 0. But what happens if one side is positive and the other side is negative? In this case, if it is negative and b is positive, we can still invert both sides, but the direction of the inequality stays the same. This is because when we have values on different sides of 0, taking reciprocals doesn't change their relative order. Now, let's apply this property to solve an inequality problem. Consider the inequality x squared is less than 4. First, we can rewrite this as x squared minus 4 is less than 0. To solve this, we need to factor it as x minus 2 times x plus 2 is less than 0. This product is less than 0 when one factor is positive and the other is negative. So either x minus 2 is less than 0 and x plus 2 is greater than 0, or x minus 2 is greater than 0 and x plus 2 is less than 0. Simplifying the first case, x is less than 2 and x is greater than negative 2. This gives us negative 2, less than x less than 2. Simplifying the second case, x is greater than 2 and x is less than negative 2. But this is impossible, since no number can be both greater than 2 and less than negative 2. Therefore, our solution is negative 2 is less than x, which is less than 2, or written as an interval, the open interval from negative 2 to 2. To summarize the 10th property of inequalities, when both sides of an inequality are positive, taking reciprocals flips the inequality sign. When both sides are negative, taking reciprocals also flips the inequality sign. But when one side is positive and one side is negative, taking reciprocals does not change the direction of the inequality. This property is essential when solving inequalities that involve fractions or when you need to divide by variables in inequalities. Welcome to this math lesson on the 11th property of inequalities. This is an important concept that helps us understand how inequalities behave when we multiply or divide both sides by a number. First, when we multiply or divide both sides of an inequality by a positive number, the direction of the inequality remains the same. In mathematical notation, if c is greater than 0 and we have a less than b, then we can say that ac is less than bc. This means multiplying both sides by c preserves the direction of the inequality. We can also say that a over c is less than b over c when c is positive, which means dividing both sides by a positive number also preserves the inequality direction. Now, let's consider the second case. When we multiply or divide both sides of an inequality by a negative number, the direction of the inequality flips or reverses. In mathematical notation, if c is less than 0 and we have a less than b, then ac is greater than bc. This means multiplying both sides by a negative number reverses the direction of the inequality. Similarly, a over c is greater than b over c when c is negative, which means dividing both sides by a negative number also reverses the inequality direction. If it is less than b, it means a is to the left of b on the number line. When we multiply both points by a positive number, like 2, every point on the number line stretches away from 0, but the relative ordering stays the same. A times 2 is still to the left of b times 2. Suppose we have the inequality negative 2x is greater than 6. We want to solve for x. To isolate x, we need to divide both sides by negative 2. Since negative 2 is less than 0, the inequality sign will flip. Dividing both sides by negative 2, we get x is less than negative 3. We can verify this solution. If x equals negative 4, which is less than negative 3, then negative 2 times negative 4 equals positive 8, which is indeed greater than 6. Our solution is correct. In this video, we will explore the 12th property of inequalities, which deals with the multiplication of inequalities. This property is particularly useful when we need to combine or manipulate inequalities in algebra and calculus. Let's start with our property. We have the following condition: if a is less than b and b is greater than 0, and if 0 is less than c is less than d, then a times c is less than b times d. Let's break down this property to understand it better. First, we have a is less than b and b is greater than 0. This means a and b are in a specific order on the number line, with b being positive. Second, we have 0 is less than c is less than d. This means both c and d are positive, with d being greater than c. When these conditions are met, the property states that the product at times c is less than the product b times d. There's an alternative way to express this property. If b times d is greater than 0, and if a over b is less than c over d, then a times d is less than b times c. Let's see how this is equivalent to our original property. Let's prove that these two forms are equivalent. We start with a over b is less than c over d. Since b and d are both positive because b times d is greater than 0, we can multiply both sides by b times d without changing the inequality direction. This gives us a times d is less than b times c, which is the conclusion in our alternative form. To get back to our original property, we can substitute a with a, b with b, c with c, and d with d, which gives us a times c is less than b times d. Now, let's see an example of how to apply this property. Example: given a equals 2, b equals 5, c equals 3, and d equals 4, let's verify if a times c is less than b times d. First, let's check if our conditions are met. 1. Is a less than b? Yes, 2 is less than 5. 2. Is b greater than 0? Yes, 5 is greater than 0. 3. Is 0 less than c less than d? Yes, 0 is less than 3, and 3 is less than 4. Now let's calculate a times c. 2 times 3 equals 6. And b times d. 5 times 4 equals 20. Is 6 less than 20? Yes, 6 is less than 20. So we verified that our property holds for these values. It's important to note that in our property, b and d are both assumed to be positive signs. This is crucial because multiplying by negative numbers reverses the direction of inequalities. For this property to work, both b and d must have the same sign. In this case, we're focusing on the case where both are positive. To summarize, the 12th property of inequality states that if A is less than B and B is greater than 0, and if 0 is less than C is less than D, then A times C is less than B times D. The key insight is that when multiplying inequalities with positive numbers, the direction of the inequality is preserved. Welcome to our math video on solving inequalities. Today we'll be learning how to analyze and solve different types of inequalities step by step. Let's start with our first example. We need to check if the following inequality is correct. -1/5 is less than 1/5. To solve this inequality, we'll apply the basic inequality rules. When we have the same denominator, we can directly compare the numerators. So we have -1 is less than 1. Since -1 is indeed less than +1, this inequality is correct. Now, let's move to our second example. We need to solve the inequality. 1 over x minus 3 is less than 1/5. This inequality is more complex because we have a variable in the denominator. When we have fractions with different denominators, we need to be careful. We cannot simply multiply both sides by the denominators because we don't know if the variable expression is positive or negative, and multiplying by a negative value flips the inequality sign. First, we need to determine the domain of the variable. Since x minus 3 is in the denominator, we need x minus 3 to be non-zero. So x cannot equal 3. Now, we need to consider two cases. Case 1, when x minus 3 is positive. This happens when x is greater than 3. Case 2, when x minus 3 is negative. This happens when x is less than 3. Let's start with case 1, where x is greater than 3. When both denominators are positive, we can cross-multiply without changing the inequality direction. So we have 1 times 5 is less than 1 times x minus 3, simplifying. 5 is less than x minus 3, adding 3 to both sides. 8 is less than x, so x is greater than 8. Now, let's consider case 2, where x is less than 3. When one denominator is negative and the other is positive, we need to flip the inequality sign when cross-multiplying. In this case, x minus 3 is negative and 5 is positive. So we have 1 times 5 is greater than 1 times x minus 3, simplifying. 5 is greater than x minus 3, adding 3 to both sides. 8 is greater than x, so x is less than 8. Now, let's combine our results. From case 1, we got x greater than 8, which applies when x is greater than 3. From case 2, we got x less than 8, which applies when x is less than 3. So our solution is the union of these conditions. X is in the domain of -infinity to 3, union 8 to +infinity. Welcome to this lesson on the 13th property of inequalities. Today we'll learn about raising both sides of an inequality to a power and how this affects the inequality's direction. When working with inequalities, we often need to perform various operations on both sides. One important operation is raising both sides to a power. Let's look at 3 different cases for raising inequalities to powers. Let's start with case 1, raising both sides of an inequality to an odd power. The rule states that if A is less than B, then A raised to the power m is less than B raised to the power m, where m equals 2k plus 1, meaning m is an odd number. For example, if we have -2 is less than 5, then -2 cubed is less than 5 cubed, since 3 is an odd number. Let's verify this. -2 cubed equals -8, and 5 cubed equals 125. And indeed, -8 is less than 125. The key insight here is that when we raise both sides of an inequality to an odd power, the inequality direction stays the same. This is because odd powers preserve the order of numbers. Now let's look at case 2, raising positive numbers to even powers. The rule states that if 0 is less than A which is less than B, then A raised to the power m is less than B raised to the power m, where m equals 2k, meaning m is an even number. For example, if we have 2 is less than 3, then 2 squared is less than 3 squared, since 2 is an even number. Let's verify this. 2 squared equals 4, and 3 squared equals 9. And indeed, 4 is less than 9. The key insight here is that when we raise positive numbers to an even power, the inequality direction remains the same. This is because for positive numbers, raising to even powers preserves their order. Finally, let's examine case 3, raising negative numbers to even powers. The rule states that if B is less than A which is less than 0, than a raised to the power m is less than b raised to the power m, where m equals 2k, meaning m is an even number. Notice that the inequality sign changes direction in this case. For example, if we have -5 is less than -2, then -5 squared is greater than -2 squared. Let's verify this. -5 squared equals 25, and -2 squared equals 4. And indeed, 25 is greater than 4, not less than. The inequality direction has flipped. The key insight here is that when we raise negative numbers to an even power, the inequality direction reverses. This happens because even powers make all negative numbers positive, and the larger negative number, in absolute value, will result in a larger positive number when squared. Let's visualize these properties on a number line to better understand why they work. Today, we're going to determine the signs of real numbers a, b, and c to satisfy certain inequalities. Let's begin with our first inequality. We want to determine the signs of real numbers a, b, and c such that ac divided by b squared is less than 0. Now, let's analyze this step by step. First, we note that b squared is always positive for any non-zero real number b. This is because the power of b is even, making the denominator always positive. Since the denominator is always positive, the sign of the fraction depends only on the numerator ac. For the fraction to be negative, the numerator ac must be negative. For a product ac to be negative, the two variables must have opposite signs. This means either a is positive and c is negative, or a is negative and c is positive. Therefore, for the inequality ac over b squared less than 0 to be satisfied, we need a and c to have opposite signs, while b can be any non-zero real number. Let's move on. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.